Let's look at one more situation. In this situation, we've got a driver of a car traveling at 90 kilometers per hour, must be a Canadian or something, and suddenly sees a barrier 40 meters ahead. The driver takes 3/4 of a second to react, and once he reacts, he hits the brakes and slows down consistently at 10 meters per second every second, which we indicate using -10 meters per second squared. The questions are, does the car hit the barrier? And the follow-up question is, what's the fastest that this driver could be going and still stop in time? In this particular problem, there's really two different types of motion. The first type of motion is just constant motion at a constant speed for the 0.75 seconds it took for the driver to react. Then the second part is the motion when the car was slowing down. Let's make a table of the different values in each of these types of motions. First, for the reacting, and then as the car is decelerating. Each of these stages has their own values for the initial and final positions, the initial and final velocities, the accelerations, and the time. For the reaction stage, the initial position is 40 meters away from the barrier. We have a couple options here. We can either say that it starts at 0 and just calculate what the final position is and compare that to 40, or we could say that the initial position is, say, a -40 meters, and if we get up to 0, then we know we've hit the barrier. Personally, I think it's easier to set the initial position to 0 and calculate the final position later and compare that to 40 and just make sure that we didn't crash. So let's say the initial position when all this started was 0. The final position of the reaction stage, we don't know. We don't know how far the car traveled before he hit the brakes. We do know the initial speed. That's 90 kilometers per hour, but that's not in a standard unit. We should convert that a second. The conversion factor for meters per second into kilometers per hour is factor 3.6. So let's calculate that quickly. 90 kilometers per hour. And we'll multiply that by 1 meter per second, which is equivalent to 3.6 kilometers per hour. And a quick division of 90 over 3.6 gives us 25 meters per second. So the initial speed was 25 meters per second. The final velocity of the reaction stage is actually still 25 meters per second because the driver just kept going. He hadn't had a chance to react yet. The acceleration during the reaction stage is 0. He hasn't hit the brakes yet, nor is he speeding up or slowing down. And the time of the reaction stage is 0.75 seconds. And we can use any of a number of equations to calculate the final position. I think the easiest in this case of constant motion is simply to multiply the time by the average velocity, which is 25. So final position is the average velocity times time, which is 25 times 0.75. And a quick calculation of that gives us 18.75 meters. It's important to know that he's already traveled almost halfway to the barrier before he's even hit the brake. We'll see if he can slow down in time. For the decelerating stage, the initial position is no longer at 0. Now he is 18.75 meters along the way. And the final position is what we're looking for. We're hoping it's less than 40. The initial velocity is the 25 meters per second. Hasn't started to slow down yet. The final velocity will be 0 once it's come to a stop. And the acceleration during this stage is -10 meters per second squared. And we don't know the time that it takes for him to stop. We could calculate that time Or we could use the no time formula to calculate the distance, since we weren't specifically asked to find time. Let's do that instead. The no time formula is final velocity squared, initial velocity squared, plus 2 times the acceleration times the distance that's traveled, or SF minus S naught. Let's do SF minus S naught. And we'll start to fill in some numbers. The final velocity is 0. The initial velocity was 25, and that's squared, plus 2 times negative 10. And the final position is what we're looking for. And the initial position is 18.75 meters. This equation is a little uglier to solve than some of the ones we've been dealing with, but let's just proceed one step at a time. 0, 25 squared is 625. 2 times negative 10, that's negative 20, times SF minus 18.75. We can move the 625 to the opposite side. That would make it negative 625 equals negative 20 times SF minus 18.75. We could distribute and then move stuff and then divide, or I think it's easier in this case to divide both sides by negative 20. That gives us 31.25, which is equal to the final position minus our initial position. If we add 18.75 meters to both sides, we get a final position of 50 meters, which means we indeed hit the barrier. So, for our follow-up question, what is the maximum speed that the driver could be going and not hit the barrier? We could go through this entire calculation again with a variable in for the initial velocity instead of the 25 meters per second. But rather than take all that time, I'd like you to look at a graph I produced that models this situation instead. In this GeoGebra graph, you can see up at the top the initial settings, the speed of 25 meters per second, the deceleration of negative 10 meters per second squared, and the driver's reaction time. And graphed behind it is a velocity versus time graph. Remember that in a velocity versus time graph, the distance is the integral of the graph, or the area that's underneath the graph and above the x-axis. That's this trapezoid here. As you adjust the deceleration rate or the reaction time or the initial velocity, you can see that the graph automatically calculates the stopping distance. It looks like 22 meters per second would be just past the barrier. That would give us a total distance of 40.7 meters. And 21 meters per second as an initial speed would definitely have a stop at time. So somewhere between 21 and 22 would be the fastest that a driver could go and still stop in time. This sort of question is really important to know, and it's often addressed in driver's education classes as the safe stopping distance. That distance was not just arbitrarily made up by some driving instructor. Instead, as you see here, that distance can be calculated, and physicists can take into account the many different situations, such as wet driving conditions or low visibility and many other different things. And after lots of playing around with graphs and equations, they've given a number that's sure to be safe in as many situations as possible. And all that comes from a healthy knowledge of using kinematics equations.